Hi everyone, it's Miss Lenorvitz, and this presentation is going to be on weathering and erosion. Awesome. As we're going through this video, feel free to pause and rewind at any point. What you're going to want to do is make sure that on your set of the notes, you're filling in the most important information so that you can use both this video and your notes as a resource in the future. There is one update that I forgot to make on your copy of this handout, and that is as we talk about mechanical weathering, you'll notice that I've listed here 4 different types. You're going to actually add in a 5th type there as well. So you'll make that change as we're going along through this video. So the first thing that we want to talk about as we're thinking about weathering and erosion is the difference between the two. They are both related to each other, but there's an important difference. So weathering is the breaking down of the rocks that have been exposed to the atmosphere or to water, so breaking into smaller pieces. And once those rocks have broken down into those smaller pieces, they then get transported. So the process of breaking down is weathering. The process of transporting is what we mean by erosion. When we think about erosion, it's usually caused by wind or by moving water. It can sometimes be caused by ice. So for example, glaciers or ice sheets will actually push and move lots of sediment from one place to another. And definitely gravity plays a role as well. So if you have materials that are up high on a cliff edge and they start to weather, they're going to get pulled down by gravity and thereby erode. So most erosion, when we think about it, that takes place on Earth happens because of water. So in terms of types of weathering, there are 3 types. We're going to start off with mechanical weathering. So mechanical weathering is when rocks are broken down into smaller pieces without actually changing their composition. So an analogy that we've used in class is if you take a piece of paper and you tear it in half and then tear that half again and tear that half into half again, you're making smaller and smaller pieces of paper. But even those tiny little shreds of paper that you have are still made up of the same elements in the same combination with each other. So when we're thinking about mechanical weathering, it's the same idea of breaking rocks down into smaller pieces. So in terms of different types, one of those types is ice wedging or frost action. And in this case, you have liquid water that is entering into small spaces in the rocks or infiltrating into the ground. And as it enters, it's a liquid. When there are changes in the temperature, either because it's a very cold climate or weather conditions change, and that water then freezes, that water will actually expand as it freezes. And when it does so, it's going to push out in all directions. So here in this picture, we're looking at the results of frost action or frost wedging that happens underneath this sidewalk here. So we're looking at the impact of water that's infiltrated, frozen, and then expanded. Here's another representation of that. So if you have water that's entered into the crack of an existing rock as a liquid, as that water cools and freezes, first of all, ice will form at the surface first, which is going to trap that water into that crack. And as the rest of that water freezes, that ice is going to push out in all directions and put pressure on that crack to expand. Eventually, that's going to end up with big rocks splitting into smaller rocks. Another type of mechanical weathering has to do with wetting and drying. So this happens when rocks that are made from clay break up, and clays will actually absorb a lot of water. When they do, they expand. When clays release that water, they shrink. And so when you have particles that are next to each other that are expanding or shrinking, that causes them to break apart. So when that happens over and over and over again, those cracks will form in different locations, and that can tend to break those particles apart into smaller pieces. So this is a big example of what would happen with mud cracks. They can actually be several inches deep. Another view of that, if you think about looking down from above, here would be the edge of a water body in the Badlands. So you can see down at the bottom of this photograph where water has most recently been, you start to see the edge of those mud cracks. And as you're looking up this photograph, we're looking at areas that were exposed to water longer and longer and longer ago. So they've been drying for longer, so you can see those mud cracks are more well developed. Another type of mechanical weathering is called exfoliation. So oftentimes big bedrock pieces are going to be covered with layers of soil or rock, and something will happen that causes that soil or rock to be moved away, exposing the underlying bedrock. all of that soil and rock that used to be on top was actually putting pressure down on top of that bedrock. And when that's no longer there, holding it in place, you get less pressure there holding those layers in place, and they start to exfoliate or peel off. So you can see evidence of that at the surface right here. We're looking at some more examples of exfoliation here. In this area, you can see that the bedrock, the soil that was there, has eroded for some reason, so it's no longer there. And there's therefore no force pushing down on top of that rock, so it's starting to mechanically weather. We see the same thing here up on the upper layers of this layer upon layer of sedimentary rock, these strata. You start to see some crumbling at the very top because there is no pressure pushing down. Same thing is going on here at this rocky cliffside. Very thin soils at the top, and actually the beach that's down here is made up entirely of little tiny pieces of the rock that has exfoliated from the top. And then a fourth type of mechanical weathering happens just from expansion and contraction, or freezing and thawing of the rocks themselves. So this is particularly true in places like deserts. When rocks are exposed to a lot of heat, the outer edge of those rocks is going to heat more quickly. The same thing is true if there are dark minerals in those rocks, they're going to heat more quickly. And that causes that material at the surface to expand. At nighttime, the opposite happens. Those rocks cool down, and the exterior is going to cool down more quickly than the interior. So you have that rock edge of the outside expanding and contracting repeatedly night after night through temperature changes. And that expansion and contraction causes the rocks to break. The last type of mechanical weathering that we're going to touch on is abrasion. And abrasion is actually both mechanical weathering as well as erosion. This happens when one rock or material rubs against another. So this can happen if rocks are tumbled in a river, in a stream, or at the edge of an ocean due to wave action. It can also happen if very fine particles are suspended in the air and moved by the wind, as we're seeing in this bottom illustration here. So all of that rubbing against each other will actually cause grooving, and sometimes can actually cause rounding of rocks as their sharp edges are worn down. The second type of weathering we're going to talk about is biological weathering. And as you probably can guess from the title, biological weathering means weathering that's been done by living organisms. It can be both chemical and mechanical. An example of that is lichen and moss, which are oftentimes some of the first living organisms that will invade a brand new area of bedrock, and they are able to live on that surface and break that rock down chemically as well as mechanically in order to get nutrients at it. Really interesting thing about this is they're the organisms that actually start making soil and makes it possible for other organisms to eventually succeed in that environment. Plant roots can also cause biological weathering, so tree roots will mechanically expand as they are growing and break apart little cracks in the rock. And those plant roots also will release chemicals as the plant is trying to access nutrients that also chemically weather the rock. And then, of course, there are all sorts of other organisms, including humans. So animals, the activity will actually, in terms of burrowing and digging and moving soil, will help to break that down further. So we're also involved in some of that mechanical weathering. The last type of weathering we're going to talk about is chemical weathering. And as you've figured out, chemical weathering happens when rocks break down and their minerals change in composition. So you have a chemical reaction or a change in properties of the rocks. One type of chemical weathering is hydrolysis, where water reacts with the minerals that are present to produce a new type of mineral. An example of that is feldspar, a particular type of rock, which when exposed to water will actually make a different type of clay. Another type of chemical weathering is one that you've worked with a great deal, which is oxidation. This is where oxygen reacts with minerals in the rock and they form a new substance. We most often think about this when we think about iron reacting with air to form rust. As you probably know, this does occur faster with water. So for example, cars in the northeastern part of the United States tend to rust faster because we have a wetter climate with more precipitation and more humidity. So that serves as a catalyst to allow those reactions to happen faster. So here we have some examples of chemical weathering of basalt. So you can see that the iron in this rock has rusted and turned red. And here we're looking at iron banding in basalt, or red beds, which are an important way for us to know when oxygen was first present on Earth. The last type of chemical weathering that we'll discuss is carbonic acid. So the carbon dioxide that's in the atmosphere can actually dissolve into water, whether it's water that's in the clouds that then comes down as precipitation as acid rain, or water that's actually in water bodies like oceans or lakes. As that carbon dioxide dissolves, it actually forms carbonic acid, which has a low pH, and that acidic environment can actually dissolve chemically many different minerals, especially those containing calcium. So things like calcium carbonate and magnesium carbonate are fairly easily dissolved by acid rain and by carbonic acid. So this gnarled rock is actually a result of acid rain falling on a limestone. Here we just have a close-up view, and you can see that the surface ends up sort of looking a little bit like Swiss cheese as droplets of water that are acidic pool onto that rock and start dissolving those minerals. They then wash away. The last thing that we're going to talk about here are factors that affect the rate of weathering. So there are three things we'll discuss. One is rock hardness, and this is exactly what it sounds. It's how difficult it is for a rock to break down. So some minerals are more resistant to weathering than others. That resistance is called hardness. And a rock that weathers easily has a low hardness, while a rock that's more difficult to weather has what's considered a high hardness. So an example of contrast there might be calcium carbonate or limestone, which has a pretty low hardness compared to something like igneous rock, like basalt has a high hardness. So those are going to weather differently. As an example here, the rock that would have stood here, where that open archway is, would have had a lower hardness than the rock that is above it at the arch. The same thing is happening here, so if you've ever been to Canyonland National Park, that is what actually caused many of those features. The second factor that will influence how quickly something will weather is surface area. So you can think about the amount of rock surface that's actually exposed. And weathering creates more surface area. And this is actually kind of a positive feedback loop. Weathering creates more surface area, and the more surface area there is, the faster the weathering occurs. Sort of analogous to if you have a cube, a big block of ice versus a whole bunch of ice cubes, and you put them out into the sun, because the smaller ice cubes have a lot of surface area exposed to that sun, they're going to melt faster than the big ice block. It's going to take a longer time to melt. So the more surface area there is, the faster erosion or weathering happens. The faster weathering happens, the more surface area is exposed. So you can kind of get the idea here is once you start to break something into smaller pieces, the surface area increases. The third factor that influences the rate of weathering is climate, and there are kind of two contrasting statements here. Chemical weathering happens faster in warm, wet climates. So that's because it's much easier for things to dissolve in water. So when you have water present, it's going to make those chemical reactions happen faster. Conversely, mechanical weathering occurs faster in cold, dry climates. Faster in cold climates because you're going to get more of that frost heaving and ice wedging that will happen. And dry climates because in dry climates you're going to have much greater wind speeds and much more consistent winds and impacts from winds. So in general, chemical weathering happens faster in warm, wet climates. Warmth will actually cause chemical reactions to go faster. The water allows things to dissolve more readily so that those reactions can happen. And mechanical weathering happens faster in cold and dry climates. So here are two examples. I'll go back to that one for just a second. In terms of dry climate, here we've got something in Australia. A lot of the weathering that happens here is mechanical, and a lot of this in this particular case is from wind with sand, so you get a lot of abrasion there. And here, the Parthenon in Athens, Greece, is a place where you have very warm, wet climate. A lot of the rocks that were used to make the Parthenon actually are fairly low hardness and dissolve pretty readily in acid rain.